Have you ever stopped and wondered how your computer is pulling off its daily magic trick? You know, streaming music with like a dozen browser tabs open while you're downloading a huge file, all at the same time? Well, today, we're pulling back the curtain on the unsung heroes that make it all possible, CPU threads.
Now really, think about it for a second. Your processor is juggling this incredible number of tasks, making it feel like it has dozens of hands. So how in the world does it manage this illusion of doing everything simultaneously?
So what's the secret? Well, it's not magic. It's a really elegant solution called a thread. A tiny, super efficient unit of work that your computer can create and switch between at just mind-boggling speeds. All right, so here's our game plan. We're going to start with the absolute basics, what a thread even is. Then we'll see how it's different from a process, weigh the good against the bad, figure out who's actually in charge of them, and finally, see how this all comes together in multi-threading models. Let's jump right in. First up, what exactly is a thread? You're going to hear me say the word lightweight a lot. And believe me, there's a very good reason for it.
Okay, so let's break this down. A thread is basically the smallest possible unit of work that your operating system can deal with. Think of a program, like your web browser, that whole thing is a process. But inside that one process, you can have a bunch of threads running all at once. One might be rendering the web page, another one's playing that video you have open, and maybe a third is checking for new messages.
Now, here's the really brilliant part. It's this perfect balance between working alone and being part of a team. See, every single thread gets its own unique ID, its own program counter to keep track of where it is, and its own stack to remember what it's done. But, and this is absolutely crucial, they all share the same code, the same data, and all the resources from the main program. And that sharing right there is the secret sauce to their amazing efficiency.
Okay, so to really appreciate why threads are such a game changer, we have to compare them to their bigger, kind of clunky sibling, the process. This is where that whole lightweight idea is really going to click.
So at a high level, a process is its own little self-contained universe. It's heavyweight because it has its own separate memory, its own copy of all the code, everything. And because of that, switching between two different processes is a really slow, expensive operation for your CPU. A thread, on the other hand, is lightweight. It lives inside a process, it shares resources, which means switching between threads is incredibly fast.
Let's get a little more specific. To create a new process, you have to make a formal request to the operating system, and that takes time. But threads, they can often be created without all that overhead. The real magic, though, is in something called context switching. Because threads share so much, the CPU can literally jump from one thread to another with almost no effort. That's the secret to modern multitasking.
So with all that in mind, you might be asking, okay, why do programmers go through all the trouble of using threads? What's the actual real-world payoff? Well, there are 4 huge advantages. First off, responsiveness. You know when a program just freezes up while it's trying to save a big file? With threads, one thread can do that heavy lifting in the background, while another thread keeps the user interface totally smooth, so you can keep on working. They also, as we said, share resources easily, they're way cheaper for the system to manage, and on modern multi-core CPUs, they allow for true parallel execution, which boosts performance in pretty much everything.
So just how much cheaper are we talking about here? Well, get this. Research on an operating system called Solaris 2 found that creating a thread is up to 30 times faster than creating a whole new process. 30. That's not a small difference. That is a staggering leap in efficiency. But of course, there's always a catch, right? That resource sharing, while it's super efficient, is also a huge challenge. Programmers have to be incredibly careful to make sure threads don't trip over each other and, try to change the same piece of data at the exact same time. This can create bugs that are notoriously difficult to find and fix.
Okay, so we know what threads are, but not all threads are created equal. It turns out it really matters who's in charge of managing them. Is it the application itself, or is it the main operating system?
First up are user threads. Now these are managed by the application itself, completely under the radar of the main operating system, which is called the kernel. This makes them super fast. But, and this is a massive catch, if just one of these threads asks the OS for something, like to read a file, the entire program just grinds to a halt. Not great.
On the other side of the coin, you have kernel threads. These are managed directly by the operating system. Now, this is a bit slower because every single action has to go through the OS. But the huge advantage is that if one thread gets blocked, the OS can just say no problem and schedule another thread from that same program to run instead. This is absolutely essential for taking full advantage of multi-core processors.
So let's just put this side by side. It's a classic trade-off, right? User threads are fast and portable, but they can't handle blocking tasks or really use multiple processors. Kernel threads are a little slower to manage, sure, but they're way more powerful and robust, letting the operating system spread the work across all the available CPU cores.
Okay, so we've got these two types of threads, the fast but fragile user threads and the slower but more powerful kernel threads. The final piece of this puzzle is how they actually work together. And that brings us to what are called multi-threading models.
The many-to-one model is pretty simple. You can have lots and lots of fast user threads, but they all have to funnel through a single kernel thread. This is efficient, for sure, but it has that same fatal flaw we talked about. If one of those user threads blocks, they all block. The whole thing just stops. Then you've got the complete opposite, the one-to-one model. Here, for every single user thread you create, the operating system creates a dedicated kernel thread to go with it. This gives you excellent concurrency and lets you have true parallelism on multi-core systems. The only downside is the overhead. Creating tons and tons of threads can become a real burden on the OS.
And that brings us to the hybrid approach, the many-to-many model, which, you guessed it, tries to get the best of both worlds. Here, developers can create as many fast user threads as they need, and the operating system intelligently maps them to a smaller, more manageable pool of kernel threads. It's flexible, it's efficient, and it completely solves that nasty blocking problem.
So, after all of this theory, what's the ultimate payoff? It's a technology that I'm sure you've heard of, hyperthreading. This is where a single physical CPU core gets so good at juggling threads that it can actually handle two at the same time, effectively tricking the operating system into seeing two processors where there's really only one.
This quote really just nails it. By executing two streams of instructions in parallel, but on a single core, you get a significant performance boost. This is really the hardware making all of our software dreams come true, letting us get way more work done in the same amount of time.
And that is our deep dive into threads, really the foundation of all modern computing performance. It leaves us with a pretty fascinating thought, though. If this clever software illusion can make one physical core act like two, what's the next trick that engineers have up their sleeves to keep pushing the boundaries of what's possible?